So now we're going to be finding the derivatives for exponentials where e is not the base, some other value is. All right, so the derivative of a to the x, right, it's going to be a lot like the derivative of e to the x. It's going to be an exact copy again. So the derivative of a to the x is going to be a to the x, except we're going to have natural log of a, right? So whatever our base is, we're going to have natural log of that value. All right, so the derivative of an exponential function is the original function times the natural log of the base. Right, now why didn't we use natural log of the base for e to the x? Right, well, if we took e to the x times natural log of our base is e, natural log of e, that's just 1. Right? So this would be the same thing as 1 times e to the x, and so that's just e to the x. All right, but natural log of a times a to the x is still going to be natural log of a times a to the x. All right, so that's why we don't have natural log of e, right? Because that wouldn't make any sense. That's just 1. All right, so these are going to be a lot like the exponentials, although the natural log of a kind of throws some unique things in there as we're trying to simplify. If we have our exponent is a function and not just a single variable, then we're going to have to take the derivative of that exponent, right? So g of x here is the exponent, a is the base of the exponential. Our derivative is going to be the natural log of that base times a to the whatever that exponent has to be, an exact copy, times the derivative of the exponent. So just like e to the x, except it's going to be multiplied by natural log of our base as well. All right, so here we have y equals 3 to the 2x plus 1. All right, so our derivative, dy dx, right, since there's a y there, I decided to use dy dx, is going to be the natural log, our base is 3, so natural log of 3 times the exact base again, so times 3 to the 2x plus 1 power, the exact copy, times the derivative, we're going to take the derivative of 2x plus 1. All right, so that would be the power rule. Different kind of power rule than what's mentioned there. This is the power rule for derivatives. All right, so derivative of 2x plus 1, that's just 2. So our derivative, whoops, I meant to put an x there. Derivative is going to be natural log of 3 times 3 to the 2x plus 1 power times 2. Oops, let me make that better. There we go. All right, so I'm going to move the 2 in front of the natural log there. All right, so dy dx equals 2 times natural log of 3 times 3 to the 2x plus 1 power. And now if we have a coefficient in front of natural log, or in front of any log, but we're only going to see natural log here, we can use the power rule. This is the power rule for logarithms. Coefficient in front of natural log or log is an exponent, right? Because log's an exponent, and what do we do when we raise power to power? We multiply exponents. So 2 is an exponent as well. So the 2 could come back up here, right? And so that would make it dy dx equals natural log of 3 squared. Right? And so we could simplify that a little bit. Now, how will your answer be if it's multiple choice? Maybe they'll just leave the 2 in front. Maybe they'll move it back up. Right? This way, you'll be able to recognize when they move it back up. So natural log of 9 times 3 to the 2x plus 1 power, and we just used a property of logarithms here. All right, and so that's our final answer here. Looks a little simpler, right, than 2 times natural log of 3, just having natural log of 9. But both technically would be correct. Right, let's do another one. There aren't too many in this particular podcast. We want to find the derivative of y equals 5 times the sine of 3x. All right, so that's going to be, I'm going to write in a different color than my question, dy dx equals, right, so we're going to have, since it's an exponential, so we're going to have natural log of 5, that's our base, times an exact copy, 5 times 5 to the sine of 3x. And then we're going to take the derivative, we're going to differentiate the sine 3x. All right, that's going to be a chain rule itself. All right, so we have dy dx is natural log of 5 times 5 to the sine 3x power. Now, if we're taking the derivative here, we're going to take the derivative of sine blop, and then we have to take the derivative as well of the blop of the 3x. All right, so that's going to give us our derivative dy dx is natural log of 5 times 5 to the sine of 3x. I decided to put parentheses there. I don't have to. Actually, I'll leave them off since I didn't put them on my question. Derivative of sine blop is going to be cosine blop, so that'd be cosine 3x. And then the derivative of the 3x would be 3. All right, let's move the 3 in front. All right, so dy dx equals 3 times natural log of 5 times 5 to the sine 3x times cosine 3x. And I just decided to use parentheses there. The 3 can move back up as an exponent, so that becomes 5 cubed. I'm running out of space here. So this right here becomes natural log of 5 cubed. And 5 cubed is 125. All right, I was going to put that over there. So dy dx equals natural log of 125 times 5 to the sine 3x times cosine 3x. And that parentheses there is kind of optional, but I did put it in. All right, and that's our final answer. There we go. There's our derivative. All right, was it that complicated? I don't think so. I hope not. All right, just got to remember the pattern, right? The natural log of the base, the exact copy, and take the derivative of the exponent. We're going pretty quickly on through these. Now we have a chain rule. A product rule. Right? We have a derivative of a product, which means we have to take the derivative of each of those. All right, so our first one is 3 to the 4x squared. The derivative is going to be natural log of 3, because that is an exponential, times an exact copy, 3 to the 4x squared. And then times, we had to take the derivative. All right, so we had to differentiate 4x squared. All right, so du is equal to natural log of 3 times 3 to the 4x squared. And the derivative there is 8x. All right, so we have du is natural log, and I could move that 8x in front. I could leave it like that, or we could simplify it. All right, you might see it like this, but let's just simplify it in case you don't. All right, so 8x times natural log of 3 times 3 to the 4x squared. I could move this back up here. All right, so that means du is, all right, so that's going to be natural log of 3 to the 8x. We could simplify the 3 to the 8 part. All right, so, and I need a calculator for that because I have no idea. All right, so 3 to the 8th power is 6,561. All right, so I'm just going to put it over here somewhere. That 3 to the 8th is 6,561. So we could make that natural log of 6,561 to the x. All right, because it was, we just moved the 8x, the whole thing back up as an exponent. All right, and 3 to the 8th, maybe I should write it out. I don't want to lose anybody. Let's move him down. Okay. All right, so this is, u is 8x natural log of 3, right? And this can move back up here. So du is natural log of 3 to the 8x power times 3 to the 4x squared. All right, and then I could simplify the 3 to the 8th power, and that was 6561. So natural log of 6561, and we still have the x on it, times 3 to the 4x squared power. So if you don't want all those terms, you can just condense that. And let's take care of v here. V was, and it'll probably be nicer to have it condensed when we get to the next part. V is 2x cubed. All right, so dv is going to be natural log of 2 times an exact copy, 2 to the x cubed, and then we have to take the derivative of the x cubed part. So dv is natural log of 2 times 2 to the x cubed, and the derivative of x cubed is 3x squared. All right, so we can move that in front. dv is 3x squared times natural log of 2 times 2 to the x cubed. And again, this can move back here if we'd like. I don't know if that one's going to look that great anyway, because that would be natural log of, we'd have 2 cubed and then x squared. So this part could be an 8 to the x squared, but I really don't know if that's any better. Maybe we'll just leave that one there. So we had the option, but I don't know if 8x squared really looks any better. 8 to the x squared power really looks any better than the way it is. So maybe we'll just leave that one the way it is. All right, so dy dx equals the first, which is 3 to the 4x squared, times the derivative of the second, which was 3x squared. Now I'm kind of wishing I'd condensed it a little bit, but natural log of 2 times, that one's okay, but let's put the parentheses around the last part, 2x, 2 to the x cubed power. All right, and then plus, because I've run out of space, the second times the derivative of the first. So 2x cubed times, and we have natural log of 2. Whoops, sorry, I looked at the wrong one. Natural log of 6561 to the x times 3 to the 4x squared. Any of them the same? Yes. So both of them have a 3 to the 4x squared and a 2x cubed. Let's pull those out. All right, so because that's really a little awkward. dy dx is equal to 3 to the 4x squared and 2 to the x cubed. And then we have what's left. We have so in the first one, we have this left. And the second one, we have just this left. All right, so we have times 3x squared, natural log of 2, and then times, oh, I can almost squeeze it in, natural log of 6561. And there is no anything special about simplifying when it's natural, when it's a log of something times. If this had been a log plus, then we can use the product rule and simplify. But I think this one is stuck just the way it is. But that's certainly a little bit nicer than what we had on the line above. So I think that's about as good as it's going to get. And these can take slightly different formats sometimes, depending on how much it's simplified. All right. So you just have to be ready to simplify when you're dealing with exponentials and logs. Just remember your rules for logs. which we'll be going over in the next part of the lesson. Oh, and actually, this is where my podcast is going to end because I'll start off with this one in the next podcast. Thanks for watching. Bye for now.